Hi, my name is Matthew Harrison. I'm a farming systems scientist at the University of Tasmania in Australia, and in this presentation I'll be talking about an introduction to carbon cycling, pathways for reducing farm-level greenhouse gas emissions, and some of the co-benefits and trade-offs that you might expect from reducing greenhouse gas emissions on farm. So if you listen to nothing else, this slide is perhaps the most important of them all because this captures the key messages from the presentation. Carbon's always cycling, but humans have disrupted the global carbon budget with fossil fuels. And that's because carbon is always being emitted from the oceans and the land. It's always being absorbed by the lands and the oceans. But what we've done is come along and dug up fossil fuels in the form of oil and gas, burnt that, and now that carbon dioxide is circulating in the atmosphere that would have otherwise been left buried beneath the Earth's mantle for millions of years. So I think the term decarbonisation is probably a little bit misguided because carbon makes up everything. It makes up you and I. It makes up the houses that we live in. It's essential for all life on Earth. What we're really talking about is defossilization, so reduced use of fossil fuels, which we're burning and contributing to global warming. The Australian livestock sector has significantly reduced greenhouse gas emissions since 2010, more than most other sectors in the country, and that's mainly been due to avoided deforestation. If we are to get to net zero by 2030, or net zero at some point, we'll have to reduce enteric methane emissions, which have been fairly well consistent over the last decade. Planting native vegetation we found that it had substantial benefits for biodiversity, and in the short term, for about 2 decades, reasonable benefits for carbon sequestration with significant reductions in farm level emissions. Anti-methanogenic pastures and conversion to sheep genotypes with finer wool, ultra-fine micron, were amongst the most prospective interventions that we co-developed with farmers. And we looked at about 30 different interventions. So these are win-win that reduce emissions, improve productivity, and can also increase productivity. The greenhouse gas emissions derived from practice changes that address an underlying economic or environmental or production deficiency generally had the most benefit. So what do I mean by that? If you've got a degraded paddock or a degraded field, restore that degradation, work out what's constraining productivity, alleviate that constraint, and then you'll get the greatest benefit. Productivity will improve, so carbon will improve, greenhouse gas emissions will reduce. If you've got a proliferation of existing weed variety, for example, can you reduce that variety? Can you get rid of that weed or that exotic pest, because that will improve productivity? So work out what the biggest constraint is. It could be environmental stewardship, it could be agri-food production, it could be an economic constraint, the exorbitant costs, for example. So how do you reduce that constraint, overcome that, and that will generally have the greatest benefit. So I'd like to spend a few moments talking about what the carbon cycle actually is. So carbon is always cycling. So you've got fluxes going into the earth and into the ocean, and you've got fluxes coming out. So things like photosynthesis, which is carbon assimilation, erosion from the land surface, as well as dissolution from rainfall, actually contribute to carbon inputs into the earth. And then you have decomposition, you have sedimentation, and after millions of years, plant residues and animal skeletons become fossilized under certain conditions. You also have losses, and they're happening all the time as well. So you have things like respiration, you have decomposition, and to a lesser extent, geological activity such as volcanoes. But one of the biggest producers of carbon emissions is due to human activity, and that's because we're digging up coal and oil from beneath the Earth's mantle and burning it, and that has disrupted the Earth's global carbon budget. So in 2023, we produced about 40.7 billion tonnes of carbon dioxide equivalents, whereas the sinks going into the land and the ocean was about 24 billion tonnes of carbon dioxide equivalents. So the net difference, about 17 billion tonnes of carbon dioxide equivalents, is added to the atmosphere, mainly due to fossil fuels. and that's created warming, and it's been creating warming for some decades now. So since about 1980, the global average temperature is about 1 degree warmer since 1980. And you might say, well, 1 degree, you get a lot more variation than that within a typical day. 1 degree is not going to make any difference to anyone. The problem with that is that climate change creates climate change. So it's actually a positive feedback loop. So a warmer atmosphere holds more moisture, and so it goes for longer before it rains, so you get more droughts. And when it does rain, the atmospheres are more laden with moisture, and so it rains in a more heavier way, so you get more extreme rainfall events, you get more heat waves, you get more bushfire risk, and you gradually get more extreme. So climate change creates climate change in a positive feedback loop. And this chart here shows the annual rain percentage area in decile 10. Decile 10 means the top 10th percentile of rainfall, and the black line shows a 9-year running average. But basically in Australia and elsewhere, extreme rainfall events are becoming more common and they're becoming more extreme. Even more so heat waves and extreme temperature. And when we look at the percentage of total land area subject to its highest ever extreme heat, in Australia, the long-term average is going exponential, which is a big problem. So Meat and Livestock Australia have the bold aspiration for a carbon neutral livestock sector by 2030, which is called the CN30 initiative. So people might say, how successful has that been? So we did a national study, a higher resolution study that has ever been done before, that accounts for all of the major land uses in the livestock sector. So this is not looking at transport and energy, etc. This is only looking at livestock. And we accounted for native vegetation, we accounted for mixed cropping, grazing enterprises, we accounted for all of those land uses, except for those red areas, which are metropolitan zones, which we excluded. And when you account for carbon sinks, so carbon in vegetation, in soils, enteric methane production, nitrous oxide production, your average net emissions are in these red zones of the country. So the Glenelg-Hopkins region, the Gippsland region of Victoria, the Midlands of Tasmania, and the southwestern area of Western Australia. Now that's because rainfall is higher in those areas, and therefore you grow more grass, and therefore your ability to put more animals per unit area is higher. Whereas your greenhouse gas emissions tend to be lower in the extensive areas, which are known as rangelands, and that's because they're more arid and you can't afford to put as many livestock per unit area. And your carbon sinks, although you grow less vegetation, are lower, the average emissions per unit hectare tend to be lower than those high intensive zones in the south of the country. And so when you separate carbon sinks and stocking rates, you see that, well, net emissions per hectare are mainly related to animal densities. They're less related to where the vegetation and the carbon is being sequestered, and more related to animal density. So that indicates that animal numbers have a greater impact on greenhouse gas emissions than carbon removals or carbon sinks. So in terms of the change that's happened over time, when you aggregate all of those emissions across the country, across all land uses and across all sectors, in terms of beef, sheep and dairy, your greenhouse gas emissions since 2010 have decreased by almost 70%, which is very significant, more than most other sectors in the country, which is really pleasing to see. But most of that has actually occurred due to avoided deforestation and regeneration. So that green bar there you can see decreasing, it's pretty much gone down to zero. Whereas the blue sectors there, the lowest segment, due to enteric fermentation, so methane emissions, have been relatively consistent over time. So if we are to get to net zero at some point, we're going to have to come up with other innovations to reduce enteric methane. So how do you quantify farm level greenhouse gas emissions? And I do acknowledge Alison Kelly at Agriculture Victoria for this next couple of slides. So we've got methane from enteric fermentation and manure, so things like beef and sheep. Then you've got nitrous oxide emissions from nitrogenous fertiliser, dung and urine and crop residues, and to a lesser extent carbon dioxide from energy use on farm, lime and urea. Now they're annual sources of greenhouse gas emissions, so a source can be zero or it can be positive. And you take away the carbon sequestered in vegetation and in soils, and they're known as carbon sinks. Now, carbon sinks can be positive or negative. So if you remove trees, that causes a big source of emissions. So it has to be, you would have to add that to your emissions then. Similarly, if you get a drought, well, then you lose soil carbon, so you'd have to add that to your annual emissions as well. So you add all them up and you get annual net farm emissions, which is your carbon footprint. So they're known as Scope 1 and Scope 2 emissions, so they're direct farm emissions. But you also need to account for upstream and downstream emissions. So they're called indirect emissions or Scope 3 emissions. So that's from things like, well, if you purchased grain, well, you have to account for the emissions in the production of that grain. If you purchased fertiliser and use that fertiliser on your crop, well, you have to account for that embedded emissions associated with that fertiliser. So a carbon footprint for any farm business is calculated on an annual basis in tonnes of carbon dioxide equivalents per hectare per year. Emissions intensity, on the other hand, is the emissions per unit product. So that's the tonnes of carbon dioxide per tonne of grain, for example. So large corporations, banks, governments increasingly want Scope 3 emissions included in carbon footprints. So you might say, well, what practice can I impose to reduce greenhouse gas emissions? Well, there's many. So you can think about reducing carbon sources or increasing carbon sinks. So to reduce carbon sources, you can fatten up animals, young animals, faster. And you can do that by improving digestibility or metabolizable energy, a bit like giving more sugar to a human, fattening them out faster and selling them off the farm earlier, so you're avoiding lifetime methane emissions. Then you can avoid methane emissions every day if you feed them low emission supplements. So there's 3-nitrooxypropanol, or otherwise known as 3-NOP. Then there's certain forms of seaweed, so Asparagopsis taxiformis. Then you have anti-methanogenic pasture species such as Leucaena and Desmanthus and Bicerella and many others. For dairies and piggeries, you've got things like anaerobic digestion of manure. Then you have animal genetics, and there's a lot of work underway for that. And some nascent technologies, which I don't think are commercially available just yet, but there's a lot of work happening on them, methane vaccines and rumen boluses, for example. You've also got nitrogen fertiliser management, more amenable to manipulation by a producer, for example, the rate, the timing, the source, and the placement. You don't want to apply a big heap of nitrogen when it's cold and wet. You don't want to apply nitrogen just on the surface when it's hot and dry and sunny, because it'll volatilise. So think about when the plant is actively growing and or just before a rain, if you're top dressing, because that will get the greatest utilisation of that nitrogen you're applying and also the greatest productivity co-benefit. Retain crop residue, so crop stubble after it's harvested. Think about renewable energy on farm, so agrivoltaics, solar panels on farm, or wind power if possible, and then collaborative supply chain arrangements as well. So grouping together with other producers can reduce financial, environmental and market risks. So what about increasing carbon removals or increasing carbon sinks? Well, restoring degraded landscapes, I've got 3 stars there because that not only improves soil carbon in a big way, but can improve productivity, fertility, improve soil moisture and water holding capacity. So it has multiple benefits restoring degraded landscapes. The question is, what is degrading it? Is it wind, water, too much grazing from a wildlife, or whatever it is? Can you alleviate that constraint? Things like improving soil fertility, if you can do it in an economical way, that will probably improve soil carbon. Clay delving can have benefits if you've got a non-wetting sand, but sometimes it can reduce productivity as well, so important to do your test strips first. Organic amendments, so things like spreading mulch or compost, will import carbon and organic matter to soils. You probably should do a life cycle assessment though, because that carbon has come from somewhere else. And if it's high in nitrogen, you can get more nitrous oxide emissions, so that offsets your carbon mitigation. Use of deeper rooted legumes or perennial pasture species, and so forth, therefore reducing cultivation. New irrigation, where you were previously rain fed. Restoring ecosystem services, so planting environmentally bespoke trees to the region. That could be reforestation, afforestation or agroforestry. You could monitor and introduce dung beetle populations, so they're really useful for restoring ecology. It's important to note that greenhouse gas emissions mitigation practices have both co-benefits and trade-offs. So they have a positive effect and a negative effect. What you want is your positive effect to outweigh the negative effect, and that's similar to most things in life. We published this in a prestigious journal called Global Change Biology in the article called Carbon Myopia, and that's freely available online, but if people want a copy, send me an email. I'm happy to send you a copy. Greenhouse gas emissions, we looked at a case study with farmers across the country. So we did 14 different case studies, and we did high resolution detailed systems modelling as well as spatially explicit modelling of these farms to see how reducing greenhouse gas emissions would impact on profit, because farms are businesses, productivity, because we have to think about the growing global population and increased food security, as well as the finite land area we have for preserving remaining biodiversity. So these case studies were spread across the depth and the breadth of the country. So there were sheep farms mainly in the south and cattle farms in the north, as is typical in most of Australia. And I mean, these farms ranged from 1,100 millimetres of rainfall per year with 750 hectares to a farm size of nearly 500,000 hectares to 163 millimetres of rain. So your ability to sequester carbon and reduce emissions very much dependent on your agroecological environment and your production system. So that's the reason that we did case studies across the country. One of those interventions that we looked at is we worked with each individual producer and we identified 10% of grazing area that could be renovated or sown with a native vegetation. So we worked with the farmers to identify where that would be, and then we modelled that growth of trees over 30 years. Now, you might say, well, why did you choose 10%? That was simply an arbitrary number to standardise the comparisons across farms because the farm sizes vary. That's actually in press at the moment. And we found that regardless of whether you're in a desert environment, whether you're in a high rainfall environment, planting native vegetation, not exotic vegetation, had substantive benefits for threatened species, plant persistence, effective habitat area, but it took at least 2 decades for significant effects of biodiversity to be realised. And the spatial configuration, remembering that we co-designed it with farmers, had a significant impact on biodiversity. So if you're planting along a riparian zone, along a river or a creek, can have more benefits than just planting a block of vegetation out by itself, for example. Connecting things, so wildlife corridors, and working with, if you've got any threatened species, how do you preserve that species in the area? So all of these contextualised factors have an effect on the relative biodiversity benefit. We also looked at spatially explicit carbon in vegetation, which is darker green is generally higher. So we found that rather serendipitously, the highest carbon sequestration was within existing woodlands and also along fence lines. So that's quite fortuitous because you're not removing productive pasture area for trees. In fact, you're sequestering carbon where you're probably not going to grow pastures anyway. So you're having a co-benefit there of reducing farm level emissions without impacting on productivity. And when you sequester, when you look at those simulations over 25 years, you see that rainfall can't explain everything. So the rainfall in the south as compared with the north is pretty similar on average, whereas you've got 110 tonnes of carbon sequestered per hectare for the farm in the south, compared with only 38 tonnes of carbon per hectare in the north. And that's because you've got higher respiration and other climatic factors influence it as well as soil conditions. So it's important to account for, not just rainfall, but soil type and other climatic factors in your assessments of carbon mitigation. So then we work with each farmer, as well as other disciplinary experts, to come up with a whole bunch of animal management, pasture management, whole farm systems changes to reduce greenhouse gas emissions. Now, I'll spend a few moments on this slide because there's a fair bit of detail in it. On the x-axis, I've got the change in annual net greenhouse gas emissions in tonnes of carbon dioxide equivalents per hectare grazed, and with the dotted line indicating a zero change. On the y-axis, I've got the change in gross margin in dollars per hectare grazed, with the dotted line indicating a zero. So the centre is the baseline. So the centre is the long-term historical baseline for each farm. Now, I plot 7 different sheep farms on this, but all of the baselines are on that 0, 0. And that's because we're interested in improving productivity and reducing emissions relative to where the farm is today. But what you can't see in this slide is that there's some big differences between existing positions of farms. So any points that fall out in this quadrant have got lower emissions but higher profits. So that's technically a win-lose zone. Any points that fall out in this area relative to the origin there have got higher greenhouse gas emissions and lower profit. So that's a lose-lose zone. Anything that falls up here has got higher greenhouse gas emissions and higher profit, which is a lose-win zone. And what you really want is lower greenhouse gas emissions and higher profit, which is falling out in this sector out here, which is technically the win-win zone. So in terms of interventions that increased emissions and reduced profit, which is probably not what you want, certain forms of altered grazing regime where stocking rate was too high and you increased emissions and resulted in excessive supplementary feeding, and use of compost instead of synthetic fertiliser. That compost that we assumed had relatively high nitrogen content and increased nitrous oxide emissions didn't really do a lot to productivity. So big differences between types of compost and mulch that you could use. In terms of the lose-win zone, so that increased emissions and increased profit, there wasn't really many interventions that did that. Increased lamb weaning rate, it tended to increase gross margin a little bit, but also increased supplementary feeding, so that's feed required from grain and hay. There was a lot of interventions that fell out that reduced greenhouse gas emissions but come at a relatively high cost. And so that was things like low emissions feed supplements, so relatively high cost 3-NOP and Asparagopsis, but generally had the biggest effect on farm level greenhouse gas emissions. And finally, those that fell in the win-win zone, even though the increase in gross margin wasn't really that much, they were still technically a positive gain, were planting native vegetation, renovating pastures with anti-methanogenic species such as Bicerella or Lotus, transitioning to lower micron sheep breeds, so you get paid a premium for finer quality wool, and fencing off bushland to prevent excessive vermin grazing. So if one farmer had too many rabbits and he fenced it off in silico, this is, and the pasture production increased, the soil carbon increased, the livestock carrying capacity increased, and so we generally had multiple benefits, and so that actually fell in there as well. Just as a side note, these error bars indicate the variability in carbon prices as well as livestock prices. So you can see that with some interventions, there's quite a bit of variation, and whereas others, there's relatively low variation, and the numbers indicate various farms. Another question that we asked was, does regen ag or does regenerative agriculture reduce greenhouse gas emissions? Well, the first thing to point out is that regen ag as a philosophy comprises many different underpinning principles. So that includes cell grazing, silvopastoral systems, so integration of livestock and trees, pasture species diversity, no cultivation, lack of synthetic inputs such as fertiliser or pesticides. So we showed that cell grazing, so high intensity short-term grazing, also known as adaptive grazing management with long spelling periods, increased soil carbon and was conducive to reducing greenhouse gas emissions relative to set stocking, which was lighter grazing for longer periods, which is sort of more conventional. Pasture type rather than pasture species diversity had a greater effect on productivity and greenhouse gas emissions. And the ability to sequester carbon really depends on where you start from. If you're starting from a high base, well, your ability to change something and increase carbon is pretty low. Whereas if you starting off from a low base, for example, 0.5 or 1% soil carbon, well, then your ability to change something and increase soil carbon is relatively straightforward. Whereas if you're starting off from a high base and you get a drought, you're most likely to lose soil carbon. So it depends on where you start. They're published in an article called Clarifying Confusions from Carbon Conclusions, and that's online, and I can also send that to people if they're interested. So were there any interventions that increased productivity, reduced greenhouse gas emissions, increased profit, increased biodiversity? Well, the greatest benefit was when an underlying contextualised deficit was addressed. So land degradation, too many pests, too many weeds, excessively high costs. How do you address that constraint? Because that results in the biggest benefit. And so that's not just in terms of emissions, but profit, biodiversity, greenhouse gas emissions, food production, everything. So, for example, fencing off sections of one farm that had too many rabbits, so fencing them off with a rabbit-proof fence reduced their grazing of the improved pastures. That improved pasture growth, that increased soil carbon, it increased livestock carrying capacity, it increased productivity, and increased profit. So it had multiple benefits because he addressed an underlying constraint. Another one, in rangeland environments, some of the existing stocking rates were too high. And for part of the time they were okay, but when you come along for a drought, your stocking rate's much too high, and that's when they run into problems. So the carrying capacity had to be attuned to the long-term climatic variability. And as soon as you did that, you reduced adult and juvenile mortality. So that's a productivity co-benefit because you got more live animals. You increase the feed available per animal because you've got less competition between animals. You increase live weight gain and you increase profitability. So that's a win-win-win-win. The final thing that I will say is the sequestration versus mitigation conundrum. And that's because if you think about sequestration over time, this red curve versus, for example, enteric methane, sequestration in carbon or in vegetation or in soils will slow over time. So if you're wanting a carbon neutral farm, your ability to do that becomes harder and harder as the trees, for example, approach maturity. In contrast, if you've got the same amount of animals and the same flock size, well, then you're still producing enteric methane emissions and they just continue up consistently. On the other hand, if you're feeding livestock feed supplements every year, well, then your ability to avoid that methane is permanent. It can't be re-released into the atmosphere once it's avoided, and it's cumulative. So every year that you do it, you're avoiding enteric methane and it keeps on going up linearly. In contrast, carbon sequestration will slow over time. So if you're relying on carbon removals to get to a net zero position, it's going to be increasingly difficult over time. The one way around that is if you do asynchronous plantings. So this green curve here is planting a whole bunch of trees at the start, and then you see carbon sequestration flatten off. Whereas if you only plant a few each year, well, then your carbon sequestration is more linear because the trees are at different growth stages and they sequester more carbon over time. But they still do gradually go down after some point. The way around that is perhaps agroforestry, where you harvest them, you sell the timber, provided it's not burnt and circulated to the atmosphere, and then you sow trees again, and you've got an asynchronous carbon removals profile on your farm. So that's really all I wanted to say. Thanks very much for listening, and I hope I'll see you next time.